Now that we have a good idea of the different types of intermolecular forces and attractive forces that apply to particles, we're ready to look at mixtures of those, in particular solutions. So we'll go through the dissolving process for solutions, talk about saturated solution solubilities, factors that affect solubility or the amount of solute that can dissolve in a particular solvent. We'll look at concentration units, and then get to some of the more interesting applications of solutions, which are the colligative properties and colloids. We first want to make sure that we're aware that solutions come in a variety of different forms. So it's not just your typical solid dissolved in a in a liquid, such as salt and water. We also have gases dissolved in liquids, liquids dissolved in liquids, gases dissolved in gases. So a simple example is air. And then even solids. We can have gases dissolved into solids. Now normally what happens here is that you end up with the solid being in a liquid state mixing with the solute and then solidifying that solid to make the solid solution. Alloys are very good examples of solutions that are solids. So we have our kind of typical image in our mind of what happens when things dissolve. So we have a sodium chloride crystal surrounded by water molecules, and the water molecules are going to come in and basically help pull apart that crystal of sodium chloride, having the water molecules surround the ions, with the positive side of the water molecule attracting to the negative ion, and the negative side of the water molecule attracting to the positive ion. From a thermodynamic standpoint, we've got three different interactions that are happening here. In the first one, up here at the top, we have an energy associated with the separation of the solute particles. So we've got to take those solute particles apart, which is in essence then breaking apart an attraction. So that's going to have a delta H that'll be greater than 0, delta H1. We've got to separate the solvent molecules to create spaces for the solute particles to fit inside of. And that delta H as well is going to be greater than 0. Again, it's always costs energy to break things apart. However, once we've broken these things apart, then we have the potential to form attractions between the solute and the solvent particles, and so that would be delta H3. And that value is always going to be less than 0, or exothermic. So it's going to give off energy whenever you put those things together. Now the crux then is, well, which cost? I mean, does it cost more energy to break all those things apart, or do we make up for that by the energy it's given off when the solute and the solvent particles come together? So these two diagrams basically describe our two situations here. So in the one on the left, we have the enthalpy of breaking the solute particles together, delta H1, separating the solvent particles, delta H2. So those are both going up in energy, and then the energy that's released when the solute and the solvent particles come together, delta H3, actually releases more energy than was put in. So here we would have a net exothermic reaction, or a delta H that was less than 0. Over on the right, we have delta H1 separating the solute particles, delta H2 separating the solvent particles, and then the delta H3, the energy that's released when those two particles come together. And notice here that the delta H3 is less than the sum of the delta H1 plus delta H2. So this ends up being a net endothermic process. meaning that delta H in this case was greater than 0. Okay. Now, what we then have to ask ourselves is, well, from nature's standpoint, then why would nature tend to do this? If we tend to go towards minimum energy, why would we proceed with something that is going to raise our energy? And the answer to that is the entropy, of course. Or S, the symbol for that. By dissolving something, you increase the entropy. Increasing the entropy is the second driving force in nature.
You too, Miss Kenny.
So in this case, the increase in entropy of having those particles then not part of that crystal lattice but spread out all over is the driving force here, even though the reaction ends up being endothermic. So if you were to do this reaction here, you would end up creating the temperature of the solution would go down because it would need to take energy from the water. So this idea is oftentimes used in cold packs and other cooling devices. All right, next we want to look at saturated solutions and solubility. So saturated solutions refer to solutions that are basically full of a particular solute. And solubility is going to be the quantitative measure of exactly how much is that makes it saturated. Now here we have kind of a neat little demonstration for us. So we have a salt shaker and some water. Notice that we have a very small amount of water here. It's 5.0 times 10 to the minus 23rd liters. And I can shake it. And it's kind of fun adding some sodium chloride to solution. And you can see that as we add it over in the upper right-hand corner here, it tells us how many ions total have been dissolved. So we have 85 sodium and 85 chloride. And let's go ahead and add some more to this. And you can see we add more and they all still dissolve in there. So we're up to 122 sodium ions, 122 chloride ions, and they're all dissolved in there. Add a few more. So we're up to 153. Add some more in there, 178. And so now we see that we actually have some of these particles that haven't dissolved. Although if you look carefully at the picture down there in the corner, they seem to be dissolving, but then others seem to be reforming. Recall that this is the process of equilibrium. So if we look up in the upper right-hand corner here, we see that the number of sodium and chloride ions tends to be around 180, 181, 179. The ones that are bound together hovering right around 23, 24, 25. And they don't always have to be in that same little clumped area there. Sometimes you can see them clumping together in other parts. But they are breaking apart, coming together in a state of constant equilibrium. So this situation here, now we have what would be referred to as a saturated solution. So we dissolved as many particles in this volume of liquid as we can. And we have some left over that are in the solid state. And they don't stop dissolving, but for every one that breaks apart, for every pair of ions that break apart, another pair of ions are going to come together. So again, we reach that equilibrium state. All right, so terms describing, quote, the fullness of the solution. So again, when it is saturated, this is a state of equilibrium. Okay, Okay, so saturated solution is a state of equilibrium where there's some dissolving, but at the same time some is also going back into solid state. If we look at an unsaturated solution, that would mean that that was all the points up to where we had solid forming in there. So there was always more room, so could fit more of the solute in there. And supersaturated is something we'll go over in class, but supersaturated is a condition where you are able to dissolve more solute in a particular solvent than you should at a particular temperature. Then we also have, and these are oftentimes these two sets of conditions or terms are confused. We have terms that describe the relative amount of solute to solvent. So the term concentrated and dilute. So something that's dilute would mean there would be a relatively small amount of solute per amount of solvent. And if it were concentrated, that would mean there would be a large amount of solute to solvent. So you can imagine making some Kool-Aid that was very dilute if you only put a small amount of Kool-Aid in the water, or one that was very concentrated where you put an awful lot of Kool-Aid in. Now, because something's concentrated doesn't necessarily mean it's saturated. Doesn't necessarily mean it's full. It just means there's a lot of solute compared to the amount of solvent. Likewise, if something's saturated, that doesn't necessarily mean that it's concentrated. There are a number of solutes that are only slightly soluble, which means that you may be able to put in less than 1/10 of a gram into a liter and have that solution be termed, use the term saturated, and you definitely would not refer to that as being a concentrated solution. Next we have the factors that affect the solubility or how much will dissolve. The table here describes different alcohols, starting with methanol all the way up to heptanol. And so you can see that the first three are all infinitely soluble in water. So you can mix them with water at all proportions. And then once you get to butanol, the solubility starts to go down until you get all the way up to heptanol, where the solubility is actually very, very small in water. Now, contrary to that, if you look at the solubility in hexane, hexane being a nonpolar solvent, the methanol is only slightly soluble in the hexane, but all of the others are infinitely soluble in the hexane. So the polarity of the molecule, the nature of the attractive forces in the molecule compared to the solvent are going to play a role here. So we'll take a look more at the solubility. As a matter of fact, we'll look at some other factors that affect solubility as well in an activity that we'll do in class. Again, here's kind of an example of the this nature of the solute and solvent. We have glucose, which is extremely soluble in water over on the right. All of the OH, the alcohol parts, functional groups to the glucose molecule make it attract very well to water molecules, whereas the cyclohexane has none of those alcohol groups or OH groups, so you don't get any kind of hydrogen bonding occurring with water. So hexane doesn't dissolve at all in water. So there are other factors that affect the solubility. We're going to look at those and look at something called solubility curves in an activity that we'll do in class.